Well, I had a vision when I first came to NASA a long time ago, which was to look at Mars the way these images show. This is Mars in 3D. What I'm showing you is, in fact, not a photographic record, but a record of 700 million laser measurements of the 3D structure of Mars. Now, why am I doing that? This seems pretty mundane and boring. But in fact, this data set, together with gravity information, shown here in color, hot colors high, cold colors low, reflects the physiography of the planet we have to deal with. We need this data to land on Mars. People, machines, ants, whatever you want. And what's so spectacular about it, really, is the tremendous magnitude of the topography of the planet. How did a planet smaller than Earth put together such a tremendous range of relief? So I'd like to stop for a minute. This is the North Polar cap of Mars, been called the Great Hockey Puck. It contains a volume of water ice discovered from this mission, the Mars Global Surveyor, now a decade ago, that is equivalent to the Greenland ice sheet on Earth. Now, if you think that's irrelevant, just remember that global climate variability on our planet can be measured through the ice sheet records of our planet. This is a critical goal in the National Academy Decadal Survey for Earth Science. Here on Mars, we have a Mars equivalent. So one of the themes that we've all come up with over the last 20 years of Mars exploration is using Mars as Mother Nature's great control experiment for understanding our own world and aspects of its destiny. And I'll show you at the end of my little talk how we use Mars on Earth to color and train our thinking. Steve Squires had a team of scientists, many of whom were experts in Earth science. Now, I also like to stop at this picture because we've all seen the photographs of Olympus Mons. Many of you in the room know the Jeopardy question. Tallest mountain in the solar system that we know about? What is Olympus Mons? Blah, blah, blah. Great stuff, okay? Anyone watch Jeopardy? I know it's early. Good, okay, just checking. But this is really more important than just a big mountain. Because that flank of stuff, and I can't point to it because I think I'm pointing to something, but I'll try to. This large escarpment here, okay, which is deeper and taller than most mountains on Earth, at several kilometers, is actually told us a story from Mars that we mapped to Earth. And what is that story? That large, big, heavy mountains made of lava collapse upon their own weight in a gravity field and produce effects. On Earth, we've discovered these around most of the big oceanic island arc volcanoes, including those like Hawaii, La Reunion, etc. If this were to happen around big oceanic volcanoes in the Atlantic, we would have tsunamis here in Maryland. So the idea that flank collapse of giant volcanoes is controlled by their mass and gravity is not something new. But we first recognized it as important on Earth by looking at Mars. Interesting how our planetary and our universe perspectives can color us. So Mars has told us about Earth. I'm proud of this data, partly because it reflects something that we needed to know. This data set I'm flying you over, Valles Marineris, was considered in 2001 by members of the National Academy as one of the few definitive planetary data sets we have as we look at our solar system. So it's very spectacular. Now, what we've learned to do as we look at Mars and as we built a program architecture is to, convert the perspective from that view in 3D to the view in 3D colored by the chemistry and topology of the surface. So here, we've combined the data from the Global Surveyor with Mars Odyssey to produce a spectacular fly-through, a scientific visualization of Valles Marineris. Now, of course, here's Los Angeles for scale. Probably should be Washington, but, forgive us, our poetic license. It just shows the sheer magnitude of some of the processes on Mars. How does the planet rip itself apart and produce escarpments and valleys that are 5 to 10 times those on Earth? A lot of people have said, well, it doesn't have plate tectonics, whatever. But this is what makes Mars so spectacular. It, as Ed Wyler has said many times, hopefully to many of you, it doesn't read our textbooks. So the fact that it doesn't, and that there is a stratigraphy in the walls of these canyons, is a reflection of the history of another world. By the way, our Grand Canyon would fit right here. Just come back from the rim. It's a great place to go. Recommended. So magnitude, topology, history. How do we see Mars? Well, the other thing that Mars has taught us is to be ready for the unanticipated. And this is what's so beautiful about science in the whole universe. We'll hear about that from Mario and John next. But as we started to get to know Mars through the mundane landscapes and the exciting ones, what did we see? We saw features that were not familiar to us. A lot of people said, all the landscapes on Mars, we've seen those on Earth. And the answer I must tell you is Not at all. And so as we got to know the surface, starting in 2004 with the landings of the rovers as part of our program, we started to see Mars at our own human scale. And this was an important step, because while Viking took us to this scale, it didn't allow us to move within the features that we wanted to understand. So what were the great contributions of the Mars exploration rover, still running now after 1,600 some days on Mars? Well, I'd like to start with where we were in May 2000. In May 2000, Ed Weiler and the leaders of NASA were posed a question: what do we do now that we just lost 2 Mars missions? 2 missions lost. Okay, Mars Global Surveyor was working, but 2 fundamentally important scientific missions lost. Well, what we did was this. We flew a pair of robotic geologists led by a great scientist like Steve Squires and his team, many 50-odd women and men, to explore Mars chemically at the scale in which geologists work. You might say, well, that sounds scary. Geologists look dirty. And in fact, they work in the dirt to read the records of planets. And I'd like to tell the story. Here's the rover Opportunity poised about a year ago at the rim of the Victoria crater. I like to tell a story because when I talk to children about Mars and the universe, I like to remind them that I have never met a rock that lied to me. Ever. As a scientist, we can read the record in these rocks, in these records, and understand, for Mars, the history of water, and thus the potential history of habitats. And by looking at the history of these rocks, perhaps reflecting an era 2 to 3 billion years ago, on a planet that may have been hospitable, one that we'd like to have been, and we believe could have been, we start to gain insight into our own history. Before the Mars meteorite discoveries and announcements by Dave McKay about 13 years ago, we didn't think to look for nanoscale records of life in our Proterozoic here on Earth. We did not think to. Ask Jerry Soffer. I'm not making this up. We thought pretty much, well, the big explosion occurred, the atmosphere evolved, and our planet became the permanent place that led to all these things. Well, we learned by looking at Mars and its rocks, through the meteorites, that may not be the way we should think about things. And these paradigm shifts are what have punctuated the history of Mars exploration. You all know we went from the Viking era to the modern Mars exploration era that we have through the rovers. Now, one of the things I'm most proud of about the Mars program, and perhaps it's not played well in the press, is the Mars Reconnaissance Orbiter, or MRO. We put this mission in place, in particular, to give us the kind of reconnaissance to play in the future. Tactical reconnaissance and strategic reconnaissance are important in science. We do it for the universe, through Hubble, through Chandra and Compton and all the great satellites that we have. We also need to do it for planets. And the scale we had seen Mars at for Viking was this background. The scale we saw from the Global Surveyor of years of craters in the southern uplands was this scale. The scale we saw from Mars Odyssey was this scale. And we realized that wasn't enough. We needed the chemical scale and the topology scale, the morphology scale, as if we were there. That will guide our planning of where we can go. And we presented the idea of this mission in 2001 to the President's Office of Management and Budget. And we said, you know, there are thousands of places we want to go, with people, with machines, however. But we can afford to go to a few. So when you're planning your summer vacation on Mars, which one can you afford to go to? I'm not being facetious. And we've used these records. Here's a patch of ice near the polar layer terrain in the north, the NPLD. Nice little thing. Looks like a horse, but it's actually 200 meters across. One of the early images from the Mars Reconnaissance Orbiter. This mission, here's the sand dunes and layers in Kendra Chasma. This mission has produced now 35 terabits of data. That is more data than every single other mission of planetary exploration in the history of NASA. One mission is in its first extended mission now. And this kind of capability is really important as we make the decision to go to the next step on Mars, or wherever. One of the things we did was fly a cooperative experiment with Italy that allows us to use long wavelength radar to see into the layers and sediments of Mars and into the ice cap. This is the North Polar ice cap with the spiral canyons. Here you see the record through sounding radar, the Charad experiment, as published in Science by Roger Phillips. And what we've seen now is the grounding line of the ice, layers that reflect the climatology of the planet over millions of years, not billions, millions. The way it loads, in fact, the upper crust, the northern crust of Mars, and whether there are lenses of potentially